Let's see how Excel is behaving by means of an equation with many variables, or let's say with a system of equations. This is one example. We have three variables, x, y, z, and three functions, f1, f2, and f3. So we need to satisfy all those three conditions. f1 equals 0, f2 equals 0, f3 equals 0. And to find the corresponding unknown x, y, and z. Let's take an example of a linear system. We know that the solution is x minus 1.05, y minus 0.38, and z 1.37. But let's see how Excel is solving it. We prepare here a table. At the very left side, we put the unknown x, y, and z, and we fill some guess values. Let's put for everybody 1. And then we build the function f1, f2, f3 as described in the presentation. So it means for every function we write the corresponding value as a formula of Excel. So for f1, 2 times x plus 3 times z minus 2. For the function f2, 6 times y minus 2 times z plus 5. And for the function 3, 9 times x minus 7 times y plus 5 times z. And on the right side we have the corresponding values, which of course is not 0 because the guess values are not the correct ones. What we have to do? First we build the square function of each one. So f1 square, f2 square, and f3 square as formulas. And finally, we make the sum of all those three square functions together. And we get this value. The values x, y, z, which satisfy the condition f1 equals 0, f2 equals 0, f3 equals 0, are also satisfying the condition sum of square functions equals 0. So we call the solver here, and we set as objective this cell to value of 0 by changing the cells y, x, and z. And we select a nonlinear method because even though the functions are linear in this case, but the relationship is not linear because we have introduced the square and the sum of the square. The solver found the solutions. All the constraints are satisfied. So this sum is 0, all the square functions are 0, all the functions are 0, so the system is satisfied by using those values for x, y, and z. And this result is independent upon the guess value because we have a linear system. Let's consider now an example where there are many possible solutions, like a nonlinear system, as displayed here, also in three variables. So we know that the system has two solutions. One is with a positive value of z and one with negative value. We need to put a guess value in the range of z positive or negative to find the wanted solutions. Otherwise, we can also input a special constraint in the solver. Let's see. The new system is represented here in this second table. As well as before, we need to put some guess values for our unknown x, y, and z. And this time the functions f1, f2, and f3 are different and they are non-linear. So we write, as before, the formulas considering the variables listed up front. And then we build also the square functions of each one and eventually the sum of the three squares. We call the solver and we set as objective this cell G14. The changing variables are B11 till B13, so x, y, and z, and we look for solutions. Okay, what we find? 0.55 for x, minus 0.55 for y, and 0.63 for z, the positive solution. But we know that there is also another solution for z negative. So what we can do here, if we are looking for that solution, we input negative guess values for all three. Let's call the solver once again. And this time we get the same values for x and y, but the opposite value for z, which is the second solution. Alternatively, we could have set within the solver a special constraint, which says that the z reference must be negative. So in this case, we do not have to specify a correct guess value because this condition must be automatically satisfied. Let's consider now another system where the solutions must be integer. For instance, we have the function of y, x, and z, 80 times x plus 60 times y plus 30 times z. This is a linear function, and this function we need to maximize subject to the constraints that the sum of the variables must be equal to 40, and then we have two inequalities: y must be greater than x and z must be greater than y. This is a typical linear programming problem where the solution is unique and the variables must be integer. Let's see how Excel is solving the problem. So here's a function we need to maximize, 80x plus 60y plus 30z. So we write this function here down, and we give some guess values to the unknowns, x, y, and z, and also we write the constraints. X plus y plus z minus 40 equals 0, y minus x greater than 0, and z minus y greater than 0. And we call the solver. So now the objective cell is G21 to be researched the maximum value by changing variable cells B18, B20, so the unknowns x, y, and z, which must be integer. So now we need to input a new constraint. And as far as the other three constraints, the equation E18 equals 0, which is the first row here. Then the second two inequalities, E19 greater or equals to 0 and E20 greater or equal to 0. And then as a solving method, we select simplex LP, so as a linear method, and we need to check the box to make unconstrained variables non-negative. And then we click to solve. And eventually we find a solution, which is x13, y13, and z equals 14. Such a problem we find quite often in the financial math when, for instance, we have to maximize a profit given by purchasing or selling some shares. And let's assume that we can buy only a limited number of shares, in this case 40. And the more is the profitability of the shares, the less you can buy. Inequalities are describing this condition. And for sure, the number of shares we can buy must be integer numbers.